Welcome back to the lecture on atmospheric escape, and let's talk now about population and observation. So let's start with this plot, which shows the transiting exoplanet population known to date. On the x-axis, you have the incident stellar radiation in units of what received by the Earth, and on the y-axis, you have the planetary radius in units of Earth radii. There are two populations of planets here. At the top, you have the hot Jupiters, and at the bottom, you have the sub-Neptunes and super-Earth. There are structures in this population that are believed to be due to atmospheric escape. The first one is the subjovian desert, which is believed to be the result of a joint effect of atmospheric escape and planetary migration. The second structure in the population is a bit less evident, and it is the radius gap, which separates at around 2 Earth radii planets that are believed to have lost their hydrogen-dominated envelope, and planets that are believed to still retain a hydrogen-dominated envelope, and there to be a gap in between. Depending on to whom you talk to or which paper you need, probably the person or the paper will tell you that the radius gap is due to atmospheric escape that is either driven by XUV radiation, so blow off, or due to boil off. Personally, I believe that it is a combination of the two. Let's now look at the effect of atmospheric escape on the evolution of a planet. Let's start with the plots on the left-hand side, and in particular on the top one. The black line shows how the mass loss rate changes with time using the energy limited approximation to estimate the mass loss rate, while the red line uses essentially hydrodynamic modeling to estimate how the mass loss rate changes with time. And the key difference here is that the energy limited approximation only accounts for XUV driven escape, while the hydrodynamic code accounts for all thermal escape processes. And you see that at particularly young ages, when the planet is young, the escape that is computed by the hydrodynamic model is significantly larger than that computed by the energy limited approximation. And this is because of boil-off, of accounting of boil-off, while at older ages, then Jeans escape becomes important, and XUV-driven escape becomes less important, and that's why the energy-limited approximation overestimates the actual mass loss rate. And this has a significant effect on the evolution of the planetary radius, which is shown on the bottom. And you see here how the planetary radius changes with time. And if you consider no escape, so only thermal contraction, you have the gray line. And then if you add escape, but computed either with the energy limited approximation or using hydrodynamic modeling, you see that the radius evolution is significantly different. At the radius that one would measure now would be significantly different, depending on how one computes atmospheric escape. But which are the main reasons for this evolution of the mass loss rate with time? Well, in particular, this is due to the fact that as the planet evolves, its radius changes intrinsically because of thermal contraction, that changes gravity, and changing gravity changes also the mass loss rate. Temperature of the planet changes because the temperature of the star changes as time passes. But what matters most is the high energy emission that changes with time. And it decreases with time. And the plot on the right-hand side shows how the X-ray emission and the EUV emission of the star decrease with time for a sun-like star. What this plot highlights is also the fact that between 10 and 10 million years and 1 giga-year, if one take a star, cannot actually know directly which high energy emission this star has, because stars are actually born with different rotation rates, and different rotation rate imply different high energy emissions. And if one has an old star that has evolved, that is actually older than 1 giga-year, it is actually not possible to reconstruct back in time how the star was rotating in the past, and therefore how strong the XUV emission was in the past. Let's come now to direct observations of mass loss. What we have seen before are sort of indirect evidences of mass loss. Now we talk about direct evidences of mass loss. And this is the first one, the very first observation of an escaping atmosphere that has been done in 2003 for the classical hot Jupiter HT 209458b. And it shows Lyman alpha, a transit absorption of at Lyman alpha light, so in the far ultraviolet. And you see this V shape of the Lyman alpha line is due to the fact that the line core is completely absorbed by interstellar medium. And there is also further complication in the Lyman alpha light because we observe it from nearby the Earth, from space, but still nearby the Earth, and there is geocoronal emission that affects the core of the line, which therefore cannot be used for transit observations. However, what is used are the wings of the line. And if one integrates the flux in transit and out of transit, and then draws the transit light curve and recovers, which is the radius of the size of the radius of the planet at Lyman alpha light, it finds out that the planet at Lyman alpha light is actually larger than its Roche lobe, which means that there is planetary gas lying outside of the Roche lobe, which implies that the planet is losing atmosphere, that there is an escaping atmosphere there. This slide shows essentially how stresses the interpretation of these observations. So one can consider different things, but one thing that one should always consider are ENAs, therefore energetic neutral atoms. You see that they generate an absorption signal. This is the number of ENA particles per meter per second as a function of velocity around the Lyman alpha line, how ENAs generate absorption in the blue wing of the line at high velocity. And this is precisely where we measure the absorption, the planetary absorption. So if one assumes that all that absorption is due exclusively to planetary material, one would overestimate the mass loss rate. Instead, if one considers also ENAs, the mass loss rate would decrease significantly. So considering or not ENAs makes a very big difference on the actual measurement of the mass loss rate that we make from Lyman alpha transit observations. There are also complicated modeling in two-dimensional and three-dimensional that have been developed to study and to interpret Lyman alpha transit observations, but not only Lyman alpha, also at other wavelengths and for other lines. And they self-consistently calculate the escape of the planetary atmosphere, so the conditions of the planetary atmosphere and its escape, and also self-consistently compute the interaction between the expanding planetary wind and the stellar wind. And these two plots, for example, show the difference that these kind of codes obtain when considering a weak stellar wind in which the planetary atmosphere is allowed to expand, and considering instead a strong and dense stellar wind in which the planetary atmosphere is then more contained and confined around the planet. So this demonstrates that using Lyman alpha transit observation is also a way of constraining stellar winds. Now, in the literature, you might read that there is a controversy between interpreting Lyman alpha transit observations using ENAs or using radiation pressure, in particular for what concerns the absorption in the blue wing of the line. Personally, I think that all physical phenomena should be taken into account and not only one of them. So both of them are definitely important and have always to be taken into account. There is also another controversy in the literature that you might read when reading papers, and one is the use of hydrodynamics against particle codes for modeling the upper atmosphere and the interaction with the stellar wind. Who uses particle simulations often says that hydrodynamics is not applicable in the upper atmosphere because the gas is not collisional. This is actually not true because the gas in the upper atmosphere is mostly ionized, and being ionized, one has Coulomb forces that make the gas again collisional, and therefore allowing to use hydrodynamics approach for studying upper atmospheres of planets. The most spectacular observation of Lyman alpha observation in general of atmospheric escape in exoplanets is definitely that of GJ436b. and which shows an almost 50% absorption from the planet in the blue wing of the Lyman alpha line of the star. And it actually shows that the planet hosts a hydrogen corona around it that is significantly larger than the size of the star. Atmospheric escape and upper atmosphere has been detected, as I said before, not only at Lyman alpha light, but also at other wavelengths. And one of them is at far ultraviolet, again in the far ultraviolet, like the Lyman alpha, but for metal lines, different kind of metal lines from different species, carbon, silicon, oxygen. And observations of HT 209-458b at these wavelengths have been studied by different authors, both the same data and different kind of observation obtained with different instruments. What is surprising, and actually is not surprising if one thinks it deeper, is that these results are pretty contrasting with each other. And the reason is that the far UV spectrum against which these lines are observed, the far UV stellar spectrum, is variable with time. It is not only variable with time because the star is variable at these wavelengths, but it is also spatially variable. So the star has spots, and if a planet happens to transit in front of a spot, the strength of this line would change. And that might induce us to believe that there is extra absorption at a given time. And this is one of the things that makes far UV transit observations particularly complicated. Therefore, one can move at near ultraviolet wavelengths where there are where the background stellar flux is certainly significantly more uniform, not only in time but also across the stellar disk. And the very first observation of this kind has been obtained in 2009 and then published in 2010 and 2012, and is that of the ultra-hot Jupiter WOS 12b. And these observations led again to the detection of planetary material outside of the Roche lobe, implying that there is an escaping atmosphere there. However, what is important here is that this absorption has been obtained not looking at hydrogen, but looking at ionized magnesium and ionized iron. And it shows that these observations showed that in this case, for this planet, escape is so strong that hydrogen drags with it heavy metals like iron and magnesium and brings them in the upper atmosphere, which can making them detectable at near ultraviolet wavelengths and allowing us to use near UV to study upper atmospheres and escape. Also, this observation led us to the detection of an early ingress that it is believed to be caused by a bow shock that is supported by either the planetary magnetic field that is intrinsic to the planet or by the expanding planetary atmosphere. It has taken time until the community realized the importance of near UV observations for studying upper atmospheres, but it has come finally. And this slide shows that the two very recent observations of another ultra-hot Jupiter WOS 121b, showing that the detection of, again, iron 2 and magnesium 2 in the upper atmosphere of the planet. But the plot on the right-hand side shows that iron 2 has been detected also in the upper atmosphere of more classical hot Jupiters like HT 209-458b, and therefore not so extreme. In this case, magnesium has not been detected, and it is believed that most likely this is because the magnesium is trapped in the lower atmosphere and is trapped inside clouds. Another way that has come up for studying upper atmospheres, and it is more accessible from the ground, and it doesn't require us to go to space, is the study at near infrared wavelengths of the helium-1 triplet. These lines form from a metastable excited state of helium-1. Metastable means that atoms that excite and arrive at this state can stay there for a while, and staying there allows us to be detectable during transit. And it has been demonstrated that this technique allows to study upper atmospheres. And in fact, there is a correlation between the depth of the transit and actually the detection of the transit at these wavelengths in the helium-1 triplet and the strength of the of the activity of the star and therefore how strong the escape is on the planet. It has been shown, however, that the use of this technique is actually very dependent on the kind of star that the planets orbit around. And in particular, it has been shown to be extremely efficient and to work wonderfully for planets orbiting active K stars, but to be less efficient for planets orbiting other kind of systems. For this reason, the UV is going to remain the most important wavelength at which to study directly and to observe directly upper atmospheres and escape. However, one problem we have is that the Hubble Space Telescope is our only UV eye that we currently have on the sky. And HST is becoming old and it will be soon decommissioned. And after that, we're not going to have anything. For this reason, there are plans for having additional telescopes that are going to be pointed and have UV coverage. The next one in line is CUTE, which is a small sat. It's going to be launched next year and is going to obtain transits of hot Jupiters orbiting different kind of stars at near UV wavelengths. And then, but this is only a small sat. And we need definitely something bigger to better study atmospheric escape. And what's going to happen is WSO-UV, the World Space Observatory Ultraviolet, which is a larger telescope that is led by Russia together with Spain, that will be launched hopefully in 2025. And it will focus exclusively on UV. And then in the further future, hopefully we're going to have larger telescope with UV capabilities that will allow us to study finally upper atmospheres and escape in greater detail. And with this, I thank you for your attention.